Yeah, join in welcoming Professor Martin Müller. He's going to tell us some old but important ideas about search and learning. Take it away, Professor.
Okay, so thanks for having me. Let me switch to presentation. More checkboxes. Okay, yeah, some old ideas about search and learning. Of course, that's a bit tongue-in-cheek, but hopefully they are all the ideas are good for now. All right, so bit of motivation. So yeah, we've been studying mostly toy problems for a long time. And I think that's true for both search and learning. And since often learning problems are even harder, that is still there's still many papers that study toy problems, right? And that's a good thing to just learn how things work in basic things. We've been talking about scaling up for decades. We've been talking about generalizations for decades. And of course, the big questions are still how, right? So Rich kind of started this trend for these tea time talks about talking about approximation for everything, right? So let's get away from the tabular case and let's be really, really serious about it. And let's try to make things work in the real world. And of course, most of you know more about learning than I do. So I've been noticing we have very similar issues in search and heuristic search as well. So I'm hoping by just comparing notes, we can make some progress. So what about the case of search, or especially what we call heuristic search? I think we've been doing great on the first problem, on the scaling up problem. So we've been scaling up to large problems literally forever, right? So in the end, that's why we invented heuristic search. If we can't solve it exactly, let's use heuristics. We've been mostly ignoring that other big problem of generalization. So I guess that's my big question, kind of my 5-year plan or 50-year plan. How can we use search if we now have these less well-defined problems where we don't have the state space given completely, where, the kind of problems RL people like to study, but heuristic search people have mostly been avoiding so far. So this is kind of the background for the things I'm thinking about. And yes, I'm talking about old ideas and I'm talking about questions. I'm not talking about solutions. So that's just where I am right now. Okay, so let's start with what are some examples of where we can actually do exact search. So this is kind of like solving things exactly in RL. We can also solve things exactly in heuristic search. Shortest path, everyone knows A star. There's many graph problems like min-cut that are very, very important in practice, and we can actually compute them for reasonably sized graphs. I put MDPs in here. If they're small enough, yes, you can solve them, right? Java is smiling. I can see the picture on the side. That's good. It's good feedback. Of course, we have solved many, many games, small ones and not so small ones, such as checkers or many end games in chess and other games. And the standard techniques that are in every textbook, like minimax and alpha beta, and the not so standard techniques that are in some other papers like proof number search that are powerful solving methods. And of course, there's these other games that are not perfect information that a lot of other people here know a lot more than me. So I'm just mentioning things such as poker and Nash equilibria. But I don't really want to say much about them because I can't. Approximate search. So I noticed Vadim is in the audience, so he's worked a lot on real-time heuristic search, and that's related to tracking that Rich was talking about. So if we cannot solve the whole problem by learning a priori, we have to adapt to changing circumstances. That's very, very close to the goal of real-time heuristic search. Where we do a little bit of search, you act a little bit in the real environment, you do a little bit more search, and so on. I think that may be good to study what is the same, what is different. And of course, we've been using approximate search methods for large and interesting games like chess and Go forever, right? And we have methods like alpha beta search with a heuristic evaluation function. We have multi-color tree search. And nowadays, we have a lot of machine learning-based search methods like AlphaZero, Mu0, and so on. So this is the classic search problem setting, and I stole this beautiful picture from the AlphaGo people because it really illustrates the problem we have with huge state spaces, right? So we often simplify and measure the problem complexity by the B to the D. So B is our branching factor, right? So we have a start state, and we have 300 possible actions or some large number of possible actions. And then after each action, it's the opponent's turn, they have a huge number of actions and so on. So the B is from one state, how many actions are there, how many successors are there. And then we have the depth D, that's what RL people call the search horizon, right? How many moves deep do we have to search until we see the result of the game, or we see the return. Right, so that's the setting. And yeah, how is this kind of search going to survive if we don't have well-specified states and things like that? That's, I think, an open question. How do we approximate? So here's one way: we use heuristics, like the name says. And the approximation means, excuse me, selective search, right? So we prune our big search tree, and there's basically only two ways. We can make our branching factor smaller, right? We ignore some actions, so that reduces the B, or we can make our search depths smaller, which means we stop before we reach the end of the game, or before we reach the true payoff at the end. And so I said we ignore some details of the distant future. And the hope, of course, is, again, we use some heuristics to evaluate states instead of keeping searching for the truth. So what are heuristics? We can use them for both states and actions. We can estimate how good they are, like there's some game state, and we compute some function, and it returns a number like 5. And higher means better, so that's a better state for us. And how do we find heuristics? Well, in the old days, people wrote them by hand. Nowadays, we use machine learning, of course. And they're basically learned by generalizing from many, many, many examples. So if we train the weights of a large neural network, it gives us this generalization. Similar states, in some sense, will have similar evaluations. All right. Here's another type of approximation, and I haven't had too much discussion, but I think this is very related to representation in RL, and that's abstraction. Right, so we map the state space to a simpler space, right? We have all these different trees, and we map them all to some green oval. That's the abstraction step, right? So from many real states, we ignore details, and we end up with some simpler abstract state. And then the same thing happens with the state space, right? From some complex state space, hopefully after abstraction, we get a much smaller and simpler state space. And then we can search the simpler space, and hopefully the solution of the simpler problem has something interesting to do with the solution of the original problem. And again, there's been a large amount of work in abstraction in many areas of computing science, but especially in search, because it is one fundamental way of dealing with large problems. I know absolutely nothing about abstraction in RL, even if it exists and how it's used. So I would love to have that conversation with some of you. Okay, so we have some success stories, of course, combining search and RL. We have the classic one, TD Gammon by Jerry Tesoro, which people usually talk about the TD part, but there is an important search part, even if it's simple and standard techniques. And search plus a machine learned neural net was amazing, strong performance for the time. And given that was a neural net for like 40 hidden nodes or something like that. All right. Of course, we have the whole series of AlphaGo, AlphaZero programs, where the search is the Monte Carlo tree search, or a variant of, and then the machine learning part is used to train that neural network, and it's used for both smooth and state evaluation. So from the standpoint of heuristic search, it's just a super strong heuristic that gives us both a good selection of moves, so we don't have to look at all of them, so that reduces the B, and it gives us a strong state evaluation. So even if we only search a few steps ahead, we can then call the neural network, and that gives us a pretty good idea of how good or bad the state is. Yeah, the learning part, it's deep RL, self-play, millions of games of the program against some slightly different version of the network. The main novelty I want to point out is the way it integrates the learning with the search. So one of the targets of the learning is actually to improve the search process itself. And that's in my eyes, the most beautiful thing about the AlphaZero architecture. So it doesn't just learn like a value function. It also learns, it doesn't just learn which are good moves, it learns which moves are the most interesting, the most useful ones to search more deeply on. And I think that's a nice, powerful new thing in AlphaZero. Search against no search, I have to have at least one such slide in every talk I give. So here's that AlphaZero slide. The network learns to play very, very well. So it learns to play about 3000 ELO, which is a evaluation scale for game players. But if you then plug it into a pretty standard Monte Carlo tree search algorithm, the search combined with the network is more than 5000 ELO. And that is a massive, massive, massive improvement. That's like the difference between the best human in the world and the weakest player at your local club. So, all right. Why does search work? I think there's two main reasons. One is search functions as an error corrector, so the backed up values from the deeper states and the minimax evaluation or averaging is better than the direct evaluation of the current states. That's purely empirical. It works in most cases. We know for many, many years there are counterexamples where deeper search leads to worse performance. And my big question, again, I don't have answers for, is can we make search work more widely for our RL, not just for games where we have the exact rules? And as far as I know, that's mostly an open problem. We just have a few starting points at this point in time. Here's the other reason I can give. Why does the search work? Well, it can improve on the offline learned general knowledge. So assume you have a good machine learning system, like the feature weights or the weights in your neural network. In the end, it's learned by some kind of averaging process, right? You see many similar but not identical examples, and that's, you train your weights by some gradient following process. And the big advantage of the search, and I don't think that will ever go away, is it can adapt to the specific circumstances. What is your current state? What are its successors? And this is unique information that you've never seen in precisely this scenario before. And again, I believe this is very close to the things Rich was talking about when he talked about tracking and what can we expect from a learning system if we let it loose on some vastly more complicated world that we're almost certain we've never seen exactly the same thing before. So there are similarities here. Okay, let me talk a little bit about another old idea. This is Dinah too. It was so Dave Silver did his PhD here, as most of you know, and this was one key element in his PhD. And yeah, the ideas again are closely related to the tracking, and it's a search-based solution. In this model, there's two types of learning, what Dave called the long-term memory and the short-term memory. So the long-term is kind of the regular Dinah, right? You do offline learning and you generalize over many examples. And in this particular case, in this application, we have location invariant features. Like if you learn something about local positions on the Go board, the same knowledge you can then apply anywhere else on a Go board. Whereas the short-term memory is something you learn for the right now, right here, not right now. So it's fast online adaptation. You ask what is different about the specific current state, and you spend a certain small learning effort to learn more about your current problem that you're solving, which is unique and different from the general stuff. And more specifically, in the case of Go, that means you're using location-dependent features. And I just try to make one tiny example to make it a little more concrete. So look at A, which is play in the middle of a 5x5 Go board, or B, play in the corner of the board. So in his system, he had only small local features up to 3 by 3 patterns. And the long-term memory just learns the average. How good is it typically to play in the middle of the board? How good is it typically to play in the corner? And for the long-term memory, this position look the same, right? This is just play in the middle. This is play in the corner. And it will learn that playing in the middle is usually better, averaged over millions or billions of training samples. Whereas the short-term memory is able to learn specifics of these positions. And of course, they're carefully constructed that here you absolutely have to play B or you lose horribly. Whereas here, B is pretty useless and A is the only good move. And so the advantage of the tracking, the advantage of the online learning is that you can adapt to these subtle differences that are very hard or impossible to learn all of them for all eternity in an offline process. Okay, so that's almost the end of my talk. What now? So of course, the reason why all these things work so well is we had the perfect simulator, right? We could do offline training, and even in the case of the online training, you can do the look ahead, right? You can see what works in this specific situation by using the simulator. So the next sentence, I hope I'm getting a lot of opposition to that, but here's my claim. I say we have almost no search techniques for the case where our world model is inaccurate, right? It's the old principle, garbage in, garbage out. If you don't know what you're searching over, why search at all? So I hope the answer is yes, we can still use search. It's still going to be very beneficial. And one small reason for that is that people do it all the time, right? We have long-term plans. I have long-term plans about going to Austria, and it's very uncertain. It's very complicated, but I'm still doing the best I can. And it's certainly much, much better than if I didn't do any planning and just try to hop on a plane in a complicated situation like now. So why do I try to talk to you about all these things? I think there's actually a lot of difficulties that are very similar for generalizing search and generalizing RL, and hopefully they can help each other. RL has a big advantage, right? You always study these model-free cases, model learning approaches. In heuristic search, we're a few decades behind that. We're just starting that kind of study. We do know search is very powerful and scalable if it works, right? So we really want to make it work. Can we have more of these kind of techniques like AlphaZero, which has this beautiful virtuous circle, right, where the learning improves the search and the search improves the learning. And that's all I had to say for today. And I'm hoping for a lot of interesting discussions. Thank you.
I think Vadim has something to say, but he should come online. Started to type. I do have one quick question. So you said that we don't have any examples.
I was hoping you would have examples.
How about MuZero?
Right. Yeah. Yeah, MuZero is a new system after AlphaGo, which tries to learn the representation and then do the search in representation space.
Yeah.
In the end, it's still based on real games, right?
I mean, in what sense? I mean, like, there is an environment to interact with, sure, like that happens
right.
with the game, but
it's able to interact. Yeah, so I think it's a big step in the right direction. Yeah, it is still bound by. No, it's a good discussion to have. Yeah, it has to learn the rules of the game first. It seems to be able to learn the rules almost perfectly from the results, judging from the results. Is it? If we change the rules from Go to some other game halfway through, would it still work? I don't know. But yes, that's definitely one of the things I was following closely and that I'm looking at. It's certainly more general than the original AlphaZero. Is it general enough?
Well, it only has a deterministic model of the environment that goes back to our previous discussion of whether you need stochastic models of the environment. So what do you think about that, by the way, Martin?
Yes, I think you need stochastic models of the environment.
Oh.
I am hoping you can learn a lot already from the deterministic ones. So I'm going to give a diplomatic answer here. Yeah. For example, in the classic probabilistic planning scenario, they have probabilistic planning with a known simulator, a known model of the environment. And some of the strongest heuristics they use are the determinizations, right? So they basically in each step have some heuristics to decide what is the most, or they just take the most likely action and then they solve the deterministic problem where you always play the highest probability action. And that seems to be one of the strongest heuristics for those searches. So, yeah, I'm kind of punting on the answer by saying I think it's a very important special case that may help the general case.
Okay.
And I mean, we kind of, when we are back to how humans do it, right? We kind of treat some parts of our world as deterministic whenever we can, right? We think this is going to work this way, and we kind of know it's going to work this way. That's when we're being deterministic. But there's certainly other parts of our world where we plan for different results. But I mean, there's complexity reasons, right? We cannot look at too many different cases. So what are your thoughts?
No, it's good.
So I want to make a few comments while Cha was thinking, which is this is really good. Yeah, for sure. And what about mu0? mu0 is I guess the famous example. They claim to be able to learn the model and then do Monte Carlo tree search with it. And I just wonder what your take is on
Yes,
mu0.
I think it's in the right direction. It's still depends on having the very powerful simulator available, right? It's still grounded in the real games, and it's very, very hard to see how to get away from that. Let me just put it that way. If you take that away, can you still do mu0 if you?
Well, I'm confused. Like mu0 has also been applied in the Atari domain.
Right.
Like, so what's the problem with that? What's wrong with this approach? I mean, like, yeah,
no,
sure.
I don't think there's anything wrong with this approach. It's just the question how general it is.
It's maybe sample inefficiency. That's the problem, or like why?
So I don't think there's anything wrong with it. I think then, let's think, for example, can we generalize it even further? I think that's the way I want to think about it, right? For example, if instead of feeding it real Go games, what happens if you feed it perturbed Go games where there's some amount of errors in it? Is it still going to be able to figure out the rules of Go? Is it going to take a lot longer? Is it going to fail in some ways? That would be an interesting research project, for example.
I guess that could also be really hard for humans.
Yes, of course. But then we also have, we cannot find out the truth by just playing millions of games and kind of testing different hypotheses, right? I mean,
or life is too short, you mean?
Life is too short for that, yes. So, I mean, I fully expect that, I mean, we know programs can solve harder problems that are out of reach for humans for these kind of complexity reasons, right? And I mean, that's one of the great powers of search. You can scale it.
By the way, so Vadim had just some comments in the chat. I don't know whether
yeah, sorry, I wasn't able to look at the chat, so I will see it now. Search inspired state abstraction MDPs.
Yeah, so we had a paper with Vadim that was really, I liked that work at the time.
Mhm. Yeah, pathology is right. I mean, that's yeah, that's a topic I mentioned just a little bit, and I know there's more work that I didn't mention.
Yeah, sure.
I try to relate it to things in RL, right? So in RL, you would talk about things like overfitting, right? More learning gives worse results, but it's not quite exactly the same thing, right? If you're looking for like Richard's research program, right? If you do more computation, does it ever give worse results? I think that's the big question. And yeah, empirically in search, usually more search gives better results, right? But for the kind of new type RL that Rich is talking about, I guess that'll be an interesting question at least to ask. Will more compute, can you develop systems that guarantee that, or at least in some stochastic sense, if you do more learning, does it learn more good things about the world rather than more random junk, right?
Mm-hmm.
I think that's a good question to ask. And again, I have no answers at all. There's recent on non-tabular learning of heuristics.
Perhaps the stochastic environments is like a very much the next question. Yeah, how do we handle stochastic worlds? Mu0, as we were just chatting a little bit about, they don't handle stochastic worlds, and you know, Martin, you just mentioned about determinism or determinizing a stochastic world.
Right.
I don't take that very seriously. I consider that's what I wrote my cryptic comment about denial. I think those guys are in denial if they think they can just, you know, take the most likely action and assume it happens all the time. That's not really taking seriously the idea of embracing approximation.
Rich, how about planning with expectation model? Isn't that similar to determinization?
Say it again.
Yeah, the echo. So just planning with expectation models came to mind as a way of doing determinization. So is that not a thing?
Yeah, planning with expectation models is something that I'm really excited about.
That's a basic like to kind of like get rid of the stochasticity, just like think about the expectations, just like one expectation. It's like there is no stochastic branching then.
Right, Chaba is correct that there is a sense in which it also making a deterministic model, but it's not just ignoring the probabilities.
Yeah, in some sense, whenever we are using sampling, we're also ignoring the probabilities, right? At least if you're only doing a small number of samples. We're not ignoring them, but we are, yeah, we're dealing with them in some limited way.
I think we're dealing with them in a fully satisfactory way, both with sampling and with expectation models. These are not ignoring, they're handling.
Okay.
Sorry, I have a question about this conversation that just happened. So, like, what is fundamentally the problem with mu0? And like, I know that it doesn't handle it currently, but like, what is fundamentally preventing it from handling it? I'm not sure whom the question is for. So anyone who knows about mu0.
Nothing.
I think in principle there's no principal problems. It just hasn't been tried. Would it be?
I mean, one immediate question is how do you learn the stochastic model, and how, like, what type of stochastic model do you want to use? And then I think that that's like a very open-ended question. And then depending on what you choose, you know, like may work or may not. So I think maybe that's the open-ended part of it.
I mean, you could maybe just try to use it for backgammon and see what you need to do. That would be the engineering approach.
So I guess the fundamental problem is that when you're learning a model, it has to somehow make sense when the world is stochastic. So you want it to be robust to stochasticity, such that when you plan with that model, you still get something reasonable. Yeah, okay.
Yeah, and I mean, there's technical issues. How do you make it produce a stochastic output? You'd have to change the architecture a little bit, but I don't think that's a major issue. There's maybe complexity issues, right? If you have important low probability events, how are you gonna learn about them?
Right. I guess the motivation for my question was I was wondering whether there's fundamentally any difference. Like if there's an algorithm that can handle large deterministic environments, is there any fundamental reason that it can't also handle stochastic environments? Because once you are committed to your model not being as big as your environment is, then your model is already losing some kind of information there. And being stochastic versus deterministic is just another way that the model is unfaithful. So, yeah.
Right, but if you wanted to produce, let's say, next states according to some empirical distribution, right? You'd have to change that, and you'd have to change the way you measure how accurate it is or not.
Right.
And yeah, that's...
Yeah, and I guess I was thinking that if your state space is truly large, then you can't have hope to produce next states. Like even a simulator can't produce next states because states cannot be described compactly.
Yeah, it's not clear. I mean, even in mu0, as far as I know, they only search 5 moves deep in the simulation, right? Which, again, they don't really explain why, but that seems to be what they're doing, and I'm sure there's a very good reason why. I mean, they do say that the errors compound, right?
Yeah.
I guess that would be a more precise way to ask your question.
Mm-hmm.
You have compounding errors in any case. Is it much, much worse in the stochastic case than in the deterministic case, right?
Right.
And if it's much, much worse, then there would be a good reason against it, right?
Right. Yeah. All right. Yeah, thanks. That pretty much answers what I was thinking.
Another difference, a fundamental difference, is that if you have approximation errors, you can give more computational resources and resolve them. But if you decide you just can't do stochasticity, then even if you throw in more resources, you can't get more accurate. You're just wrong. It's very different.
Okay, I don't know how we're doing on time.
So yeah, you're officially done with time, but people can stay back and ask more questions or continue this discussion if they want.
Yeah, I'd be happy to hang around.
Yeah, and other people can get on with the rest of their day. Thanks for joining us today. We'll see you tomorrow again at the same time, 4:15.
Thanks for organizing this.